Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the periodic table. Today we will begin with lecture 10 from the course, but make sure you have watched the previous ones before viewing this one. Well, I hope you are all clear about what is atomic radius, what are the types of atomic radii, and what are the trends of atomic radii in the periodic table. Carrying the discussion further, we will be discussing about the ionic radius in this lecture and then the trends of ionic radii in the periodic table. So quickly revising, first of all, what are ions? Ions are formed when a neutral atom gains or loses one or multiple electrons, and based on the loss or gain there are going to be two types of ions. First the cations and second anions. What are cations? They are positively charged ions, whereas anions, they are negatively charged ions. Cations are formed by the loss of an electron or more than one electron as well, and whereas we have anions being formed by the gaining of electrons. For example, you can understand this with the example of sodium. We have the electronic configuration for which to be 1s2, 2s2, 2p6, 3s1. So when sodium loses one electron, it is going to form a cation corresponding to it, that is the Na plus ion. So here the electronic configuration is going to be 1s2, 2s2, 2p6. Similarly, we have fluorine atom, the electronic configuration of which is 1s2, 2s2, 2p5. And when it gains one electron, it forms the fluoride anion, which has the electronic configuration of 1s2, 2s2, 2p6. So I hope this is clear. So now let us understand what is ionic radii. So we can define the ionic radius to be the effective distance from the nucleus of an ion up to which it has an influence in the ionic bond. So we have studied the forces of attraction between the various atoms while we were calculating the atomic radii, that is the covalent bond, the metallic bond, the van der Waals forces of attraction. One left was the ionic bond, right? So this is the bond between the two ions, that is the cation and anion, and to calculate the radius of an anion or a cation, what are we going to do? We are going to calculate the internuclear distance between both of them, and this is going to give us the radius of the cation and anion if one of them is known to us. Okay, so we have the internuclear distance to be the sum total of the radius of the cation and the radius of anion, and these can be calculated just in a similar fashion as the calculations of atomic radius is done by the basis of the diffraction experiments. So now let us see how the atomic radius of the atom, this is related to the radius of the ion it is forming by the loss or gain of electrons. First see the difference between the atomic radius and the radius of the cation. We have sodium 186 picometer the atomic radius, and Na plus the ionic radius is 95. So what does this mean? That the radius has decreased when the atom is forming a cation. Similarly, you can see for potassium, beryllium, magnesium and calcium as well that the ionic radii has decreased. So what does this mean is that the size of the cation, this is smaller than the neutral atom from which the cation is being formed. Why is it so? Well, the number of protons in the ion, this is going to remain the same as it was in the neutral atom, but the number of electrons has got reduced. Hence, the nucleus is pulling lesser number of electrons, and eventually what does this mean is that on a single electron there is a greater force of attraction of the nucleus, and hence the electron cloud, this is going to be pulled closer to the nucleus, and the size of the cation is going to be less, right? And in some of the cases you will see that the whole outer shell has disappeared after the removal of the outer electrons. For example, when we form Na plus from Na, there is going to be the loss of the whole of the outer shell, and this is also going to be one of the reasons where the size of the cation is going to be less than that of the neutral atom. So next, let us see the difference between the size of the neutral atom and the anion. Here you can see fluorine having the atomic radius 64 and the fluoride ion having the atomic radius of 186 picometer. So what does this mean? That the radius has now increased. Similarly, you can see for chlorine, bromine, iodine, oxygen, nitrogen and the corresponding ions that the ionic radius for the anions, this has increased in comparison to the neutral atom. Now, why is this so? Think on the similar lines. The number of protons is going to remain the same, but the number of electrons has increased, right? So, if this has increased, this means that the nucleus is going to pull more number of electrons. Hence, on each electron, there is going to be a lesser force of attraction. Hence, the electron cloud, this is going to move farther away from the nucleus, and hence the size of an ion, this is larger than the neutral atom. And you can say now that if we have the same atom and the anion formed from it and the cation formed from it, what is going to be the relation? The anion is going to have the largest size, then the neutral atom, and the smallest size is going to be that of the cation. Now let us see what are the general trends of the ionic radii in the periodic table. So we have the ionic radii to be increasing down the group due to the successive addition of the new orbits. So this is just similar onto the lines that we have discussed the atomic radii as well. Down the group, the atomic radii increase, down the group, the ionic radii also increase. Then in a period, what does happen? In the period, the atomic radii, they were decreasing from left to right because of the increase in effective nuclear charge. Same way, the ionic radii, they are also going to decrease in the period from left to right. And what about the transition metals? The ionic radii, in the case of transition metals, they are going to be different in different oxidation states. So the transition metals, they show a variety of oxidation states, as you will be understanding further in the course, and for each one of them the ionic radii is going to be different. In general, what we can say is that the ionic radii, they are going to decrease with increase in oxidation state. For example, if we compare Fe, Fe plus 2 and Fe plus 3. So the parent atom, this is going to have a size larger than the cation that we've already discussed. And now we are saying that if we see the oxidation state, Fe plus 2 and Fe plus 3. So when the oxidation state is going to increase, the ionic radii decreases. So we have Fe plus 2 to be having an ionic radius greater than Fe plus 3. And if the oxidation state is the same, then how do we see the trend in the periodic table? So we see that in the period, in case of the transition metals, we are discussing that the ionic radii, they are going to decrease with increase in nuclear charge. So you can see the 3D series, all the metals having plus 2 oxidation state, and with the increase in the nuclear charge, that is when we are moving in the period from left to right, the ionic radii with the increase in nuclear charge, that is decreasing. For copper and zinc, again you are seeing that there is an increase in the radius because of the interelectronic repulsions that had increased and the value of the shielding effect that had increased, right? So next very important term related to the ions that you have to understand is the isoelectronic ions. So these are the ions of different elements having the same number of electrons, but they differ in the magnitude of nuclear charge, right? For example, we have the sulfide ion, chloride ion, K plus and calcium 2 plus ions. So all of them, they are going to have a different nuclear charge corresponding to the atomic number of theirs. And now if you see the number of electrons in all of them, this is going to be the same. The sulfur atom, this gains 2 electrons and hence it is going to have 18 electrons. Chlorine atom gains 1 electron. So 17 plus 1 is going to be 18. For potassium, there are going to be 19 electrons in the neutral atom. It loses 1 electron, hence 18, and calcium 2 electron loss is giving again 18 electrons. All of them having the same number of electrons, hence they are called as isoelectronic ions. Now what about argon? Having the same number of electrons, that is 18. This is isoelectronic with the sulfide ion, the chloride, potassium and calcium ions. But the difference is that this is a neutral atom. So can we call it an isoelectronic ion? No, we cannot. So we have coined another term which is called as the isoelectronic species. And here we can have atoms and ions of the different elements which have the same number of electrons, but they differ in the magnitude of nuclear charge. Only difference is going to be isoelectronic ions, they are all ions, and isoelectronic species, they can be neutral atoms as well. As you can see in the following example, we have the nitride ion, the oxide ion, fluoride ion, neon, this is an atom, then sodium ion, magnesium ion, aluminium ion. All of them, they are having 10 electrons each. The nuclear charge in them is different and they are together called as the isoelectronic species. So now let us understand the relationship between the ionic radii of these isoelectronic species, and this is a very frequently asked question in the examination. So the isoelectronic species, they have the same number of valence electrons. They are going to differ in the nuclear charge. For example, you've already seen that O2 negative, F negative, Na plus, magnesium plus 2, they have the same number of electrons, that is 10. But if you see the size of these, so we see that the nitride ion, this is having the size of 171 picometer, oxide 142 picometer, fluoride ion 136 picometer, Na plus 95, magnesium plus 265, aluminium plus 350 picometer. So you are not supposed to remember these values, but you can understand that the ionic size, this is decreasing with the increase in nuclear charge. The number of electrons is same, the nuclear charge is increasing and the size is decreasing. So what do we interpret from this? Let us understand. So you can understand this variation of ionic size among the isoelectronic species by just simply understanding the Z by E ratio for them. Okay, what is Z? The nuclear charge, E the number of electrons. Just make a ratio of all these. Okay, neon, well, this is not going to be the ionic size, this is the atomic going to be. The ratio is just giving you the atomic size, and we will not be able to compare neon over here because this is going to be represented by the van der Waals radius, and for the rest of them we are having ionic radius. So we will not be comparing isoelectronic species. In fact, we will be comparing isoelectronic ions over here. Okay, so this Z by E ratio, this is going to represent the effective nuclear charge of any ion. And this is just a representation, not an exact value. And we find that more is the Z by E ratio, smaller is the size of the ion. That you have already seen in the previous table as well, that when the nuclear charge was increasing, what did you get? That the size was decreasing. So just if you calculate for any ion the Z by E ratio, compare the two ions, whichever is having more value of Z by E ratio, smaller is going to be the size of that ion. So comparing all of these, the Z by E ratio for aluminium plus 3 is maximum. So the small is going to be the smallest over here. So aluminium plus 3, then magnesium, then sodium ion, then fluorine ion, then O2 negative, and then Ne3 negative. Okay, so I hope you can understand this, that more is the Z by E ratio, smaller is going to be the size of the ion. So with this Z by E ratio calculation, you can tell the size of the various isoelectronic species. For example, if you have to compare Na plus and Na, okay, the cation and the parent atom. So we have Na plus, the Z by E ratio to be 1.1, and sodium it is going to be 11 by 11, that is 1. So which is more Z by E? It is for the Na plus ion. So more is the Z by E ratio, smaller is going to be the size, and we have Na plus to be smaller in size than sodium, that we have already seen as well. Similarly, you can do that for chloride ion and chlorine atom. The Z by E ratio for chloride atom is going to be less than 1, and for chlorine atom it is 1. So again, chlorine atom, the Z by E ratio is more. This means that that is going to be smaller in size than the chloride ion. Okay. You can do this comparison for Fe, Fe plus 2, Fe plus 3 also. You will find the parent atom to be the largest in size, even from the Z by E ratio. And similarly, you can do this for O, O negative and O2 negative as well. So what are we going to learn from all this is that the size of the cation, this is smaller because of more Z by E than the parent atom. The size of the anion is bigger than the parent atom because of lesser Z by E. More is the magnitude of positive charge, smaller is the size of the cation. More is the magnitude of negative charge, bigger is the size of an ion. Right? Now, we have finished this lecture over here, but there are certain facts that you have to remember, and they are going to be very important for your problem solving. Okay, so the first thing that you have to remember is that the lithium ion, this is greater in size than Mg plus 2 ion. In fact, the lithium atom, this is greater in size than magnesium atom. Okay, so just remember, while you're giving the order of various ions, you have to place the lithium ion greater in size than the magnesium ion. Similarly, you have to remember that the H ion, the hydride ion, this is larger in size than the fluoride ion. Okay, and we've already discussed that aluminium, this is larger in size than gallium. They almost have similar sizes, but aluminium will be having a size larger than gallium. Okay, so then the largest cation is going to be cesium positive, and the smallest cation is H positive. The largest anion is I negative, but the smallest anion is not H negative, this is F negative. Okay, so these are certain things that you please do remember while you're solving your questions. So that would be all for this lecture. I hope you've understood everything quite well. But in case there is any doubt, always most welcome. Mail us at h2ochemistry@gmail.com or put it in the comment section as well. And if you've liked the lecture, only one appreciation, please do click on the like link, and also do subscribe to our channel H2O, and click the bell icon to get a notification as and when we put up a new lecture for you, a new course for you. We will be meeting again for the next lecture, which is going to be on another very important topic, that is the ionization enthalpy. So see you again. Bye bye. Have a nice day. God bless you.